However, this feels really unlegible to me. Like, can you guys see this?
I can see it, but it's definitely fuzzy.
Yeah, it's fuzzy, right? That bums me out so much. I was hoping that would be like this. I was hoping this would be the new thing, because then I won't have to run out of space on the whiteboard and a whole desk to work with. But anyway, we're back to the whiteboard. I have solutions. I have contingencies. So the point is, today we're talking about. Thank you for your honesty, by the way, Camille. Today we're talking about strong mathematical induction. And I have absolutely racked my brain trying to think of a nice physical example of this, but it's very hard. So strong mathematical induction is compared to weak mathematical induction. And let's go over what the heck weak mathematical induction was. Weak mathematical induction always went like this. To prove that some claim was true, P of n, for every number bigger than or equal to A, right? What you did is you first prove it for A, and then you showed that for anything bigger than or equal to A, if it was true for n, it would be true for n plus 1. So basically all you showed is that you found some number A that was true, and you proved that for everything, including that and after that, if it's true for this, it's true for the next one. And it's true for the next one. So therefore it's true for the next one, the next one, the next one. And this was the whole thing we had with the dominoes, right? Where you had a whole line of dominoes here, right? And the whole thing about dominoes, the whole reason why we love that example so much, or at least I love it, but I hope I can speak for you and say you guys also love it. And that is that because this is a very nice physical way to think about what's actually happening in induction. What's happening is once you prove the base case, once you prove that that's true, well, this inductive step tells us that then P of A plus 1 is true. And then P of A plus 2 is true. And then P of A plus 3 is true. And then P of A plus 4 is true. It's this domino effect. Everything after that falls into place. So everything I'm talking about here is weak mathematical induction. Why is it called weak? Well, because people like to make fun of it. But the reason is because of in weak mathematical induction, we use only P of n to prove P of n plus 1. So notice, like, I'm going to make A just equal to 1, so we're talking about something in particular here. But you can start at anywhere is the point. Like we started at 13 for that one proof the other day. So we have 1. So like assuming the base case was 1, we can have something like this. So notice that to prove P of 3, all we need to know is P of 2. To prove P of 4, all we need to know is P of 3. To prove P of 5, all we need to know is P of 4, right? The way that weak induction works is we use just P of n to prove P of n plus 1. But here's the really weird thing about this. Like, if we're here in this step, like if we're imagine the dominoes falling down and we got to P of 4, and we're trying to prove P of 5. Well, we don't only know P of 4 is true, we also know P of 3 is true, we also know P of 2 is true, we also know P of 1 is true. So there's no reason not to necessarily use these to help us prove P of 5. For dominoes, it doesn't really matter, right? Because for dominoes, like if this is the first, second, third, fourth, fifth, sixth, it doesn't really matter what happens to the first 3 dominoes. If the 4th one falls, the 5th will fall. But we could think of some more convoluted examples maybe, where in order for the 5th to fall, maybe the 3rd also has to fall. Like, like the examples I was trying to think of, I was trying to draw these weird things where it was like, imagine like the first domino has to fall to hit the second domino. But then like, maybe the first domino is really tall, and then like in order for the 3rd domino to fall, like it has to get hit by the first and the second, something like that. Or maybe like, I don't know, like I was trying to think of wires, like maybe like 1 goes and does 2, but then like to prove 2, like 3, you need both of them. I don't know. The point is, I hope you could kind of imagine an idea that maybe to show that like the 5th case happens, it would be useful to know that not only the 4th, it might be useful to know that also the 3rd happens, or maybe the 2nd happens, maybe the 1st happens. So the idea is in strong induction, we use P of 1 and P of 2 and P of 3 all the way out to P of n to prove P of n plus 1. And it's called strong induction because this is much more information, right? We're using P1, P2, P3 all the way out to Pn. We're using n things to just prove one thing. Whereas in the dominoes and weak induction, we just use one to show the next. Whereas in strong induction, we use everything before it to show the next. Which, why not, right? Because, you know, the way strong induction would work is you have P of 1, and as a base case, you know that's true. And then you use that to prove P of 2. But then the way strong induction works is instead of using P of 2 to prove P of 3, why just use P of 2? You can also use P of 1 in that. So you use P of 1 and P of 2 to prove P of 3. And then to prove P of 4, you get to use P of 3 like usual, but you can also use P of 2, and you can also use P of 1. And to prove P of 5, you can use P of 4, you can use P of 3, you can use P of 2, and you can use P of 1. Does the idea make some sense? Yes? No? How about this? We'll do an example. We'll do a beautiful, nice example, and then maybe you'll see what I'm getting at more here.